The phasors, as you will recall from 240, are a shorthand for sinusoidal signals. So, if I have a sinusoid, like A cosine of omega t plus phi, I can represent that as a phasor by taking the amplitude and the phase and writing them thus. Now I can reverse that process by just multiplying by e to the j omega t, taking the real part, they get back out a cosine of omega t plus phi. Now I can do all the same things with the sinusoidal field. So I have a time-varying sinusoidal field like this one. I can write this sinusoid as a phasor by again taking the amplitude and the phase, writing it like that. I can still change it to a magnetic field just by using the right-hand rule and Ohm's law as before. And this portion is exactly the same. Now if I want to write a conjugate, all I have to do is change the sign of the phase. Now it's a conjugate. All right. Now this brings us to finding the time average Poynting vector. So we can do it the hard way, the way we've talked about before, or we can do it an easy way with phasors. But to understand the easy way, we need to look at a trig identity. We're going to develop it by looking first at two functions. Let's say that we have, so the trig identity is this. I should just say that first. Trig identity is cosine of A times the cosine of B cosine of A minus B plus B. Okay, so to illustrate how that might work, let's say that we take A cosine of omega t plus theta, and we multiply that by B cosine of that will be equal to B over 2 quantity cosine of theta minus phi, because that's this multiplied this. Omega t's cancel out. Plus of adding plus theta plus phi. Now, if we wanted to take those two functions, which are a of t times b of t, and if we wanted to find the time average of the product of those two sinusoids, we would just take the time average, 0 to t, d, tau, all this stuff. Now, this is a cosine, so it averages out to 0 over one period. This is a constant, so it comes out of the integral, and you're left with b over 2 cosine theta minus phi integral, or 1 over t, integral 0 to t d tau of 1. Multiplier, that's just t, big, just goes to 1. So we find that the average of a of t times b of t is just equal to b over 2 cosine of theta minus phi. Now, we can rewrite that as 1/2 the real part of a e to the j theta times b e to the minus j. And that, as you may have guessed, is the same as 1/2 the real part of a phasor Now, if we're doing something like E cross H, and these are time-varying sinusoids, we can actually use this very same thing. We go 1/2 the real part of E phasor cross H phasor conjugate. So let's see what this looks like. This is 1/2 real part of E naught e to the minus jkz in the example we gave before times E naught over eta naught e to the plus jkz, plus because it's a conjugate. These terms actually cancel, and you're just left with E naught squared over eta naught, which is real, so it just pulls out. You just get 1/2 E naught squared over eta naught. Now it was a cross product, so that cross product is what then gives us the direction, which is the direction of propagation, which for an x-directed E field and a y-directed H field gives us a z-directed propagation. That then is the cross product of E and H, or time-varying Poynting vector. And that in general is how you're going to find it. Find the time average Poynting vector. You just take 1/2 the real part of E conjugate, E phasor, H phasor conjugate in the direction of propagation. Or 1/2 E cross H conjugate. And done.